again. Yeah, so the recording started and now I'm sharing the screen again. And so what we had, we're just talking about was down here, seeing these different pictures of gradient descent. And then there was just a question about the step size. And I was saying that this variable right here, this eta variable, yeah, so this Greek letter is pronounced as eta, eta. And this is one of the common Greek letters that's used for this variable. But other variables that you'll see sometimes are alpha and gamma are also popular variables to use here. It's essentially always going to be a Greek letter that you'll see right here. And then in English, this is sometimes called the step size or the learning rate. And these are synonyms of each other. The step size is a little bit more generic, that can be used for any f function, but when we use the word learning rate, then it's specifically in the context of a data mining algorithm and not in some other sort of optimization context. So speaking of the data mining context, this f function for us is what it's going to look like is our training loss at whatever our input w is. So this is really f of w, f of w equals the training loss of w plus lambda times whatever regularization you're using for w. So this f of w is the thing that, I'm gonna scroll up here just for a second. This f of w is the thing that sits over here to the right of the argmin in this regularized loss minimization function or empirical risk minimization. It's a great question. Any other questions so far?
Well, in the video, the learning rate was a factor in the step size, but then you just said that it's synonymous. So I'm just maybe a little confused there, because in the video, the step size was just the parameter times the learning rate or something.
Let's see. So yeah, this variable right here, it's always going to be a scalar. So this scalar right here is sometimes called both the step size and the learning rate. One thing that's maybe you're referring to with this step size is that the actual distance between, say, W0 and W1 down here is not, it's a function of both this this eta value and the magnitude of the gradient right here. Oh. So if the actual distance that we're going to step, say from one point to the next, is this value times the magnitude of this. And so here at W0, because we're really far away from W star, the magnitude of the gradient is going to be very large. And so we're going to take a really giant step. But here down at W2, because we're really close to the minimum, we're going to take a really small step. And so the length of the distance that we actually step will change based on what point we're actually at, but the phrase step size typically refers just to this scalar value right here and not to the actual product of that scalar times this gradient.
Thank you.
Great questions. Any other questions so far? Okay. So one really important question is, like, how do we actually select these eta values? And this turns out to be really of like fundamental importance, because if you don't select this value correctly, then we're not guaranteed to actually get to the minimum down here. So let's imagine again with this plot right here. I'm going to use blue this time. With this plot right here, if our eta value is really large, then we continue going in this direction to the right, but we'll go so far that we overshoot W star and come like way over here. And in fact, this W1 value is now greater than this W0 value because our eta was so large. When that happens, at W1, the magnitude now is guaranteed to be bigger than the magnitude of W0. The magnitude of the gradient at W1 is guaranteed to be bigger than the magnitude of the gradient at W0 because the function is farther away from the minimum. And so when we again take the gradient here, it'll move us to the left, but it'll move us even farther away from the minimum. And so we'll get a value like W2 up here. And when this happens, we would say that the model is diverging in blue, or the algorithm is diverging in blue when it's getting farther and farther away from the minimum each time we run it. Whereas in this red situation, we're getting closer and closer to the minimum. And so we'll say that the algorithm is converging. And we saw this again in the PageRank problem, was that sometimes PageRank could diverge and sometimes it could converge based on the properties of the P matrix and its eigenvalues. And here in gradient descent, the key thing that controls whether the algorithm will converge or diverge is the value of this eta right here. So we're going to look next at this corollary 14.2, which tells us all of the conditions that are sufficient conditions to ensure that gradient descent converges. And so this is one, it follows the same format of the things that I'm having you do for the pre-lecture work on Wednesday. And hopefully our discussion about this one will make it so that you can work through those other theorems and corollaries, and they'll make a little bit of sense while you do it. But what this says is if we let F be convex and rho Lipschitz, and then run gradient descent, so GD for gradient descent for T iterations with eta equals B squared divided by rho squared T. And so I'll talk about this more in a second after I've written everything down. Then F of W bar minus F of W star is less than or equal to B times rho divided by the square root of T. So here, this is an example of a result that I would call a pure optimization result. And it's a pure optimization result because nowhere in here are we talking about training sets or test sets or the error of a learning problem. And in particular, we're just talking about a function f, which is an arbitrary function. Could be a function like the training loss, in which case we would be in the situation of a learning problem, or it could be some other arbitrary function. The rho value here is applying to f, and again, this is sort of the measure of how linear this function f is. So convex and rho Lipschitz. So this result would apply to this graph right here, this Lipschitz graph, but it would not apply to this graph here because this is not a Lipschitz function, and it would not apply to this graph here because this is not a convex function. And then this is the condition about what eta has to be set to in order for the model to converge. And really what we want to be paying attention to is how each of these variables, sort of the trend about how it affects eta. And so again, this rho value here is rho value here, how Lipschitz the function is. The t value here is how many total iterations we've done. So if we're doing more iterations, then we need fewer, we can use smaller step size. This b value here, though, is something that, that we haven't talked about yet. And the first thing that I want to do is talk about it informally, and then I'll define it formally. So coming back up here, the b value is the sort of range of w parameters that we're going to search over. So if I'm starting my w naught here, and I know, say that w star is somewhere contained within this set right here, but I don't know where, this size right here is going to be my b value. So if somehow I had special knowledge of the problem where I could say only search in this region here and have this smaller b value, call it b prime to distinguish it from this. If somehow I was able to constrain my search space to be this smaller region b prime instead of this larger region b, then intuitively, since there's less region for me to search, then the search will go faster. So to make that formal, I'm going to define exactly what this b parameter is. And what it looks like is we have w star equals the argmin over w such that the norm of w less than or equal to b. And then the thing that we're minimizing is still the f of w right here. So the only part that this b part comes in is this definition right here, or this range right here that we're doing the minimization over, and it tells us how big this w parameter can possibly be. In the case of these single dimensional examples like this, that w parameter can just be the absolute value, but typically in the multi-dimensional case, this w parameter is the L2 norm. But the L2 norm is equivalent to the absolute value in the one-dimensional case. So that's the B, the rho, and the T about how to determine this eta value. But the last thing that we need to talk about is this W bar right here. We haven't talked about a W bar yet. And so the way that's defined is W bar is equal to the sum from I equals 1 to capital T of all our WIs, and then divide by T. So W bar is the average of all the W's. And this is a common notation that you'll see, people putting a bar on top of the variable to indicate it's an average somehow. So are there any questions at this point?
So the above formula, the W star minus argmin, is that for determining B?
So this formula right here defines what B is. It's the range of the W's that we're searching over, the maximum size that a W value could possibly be. This formula right here is the actual result of the corollary, and it's saying that the distance between F bar and F star is guaranteed to be smaller than this. So if we increase the number of iterations, increase T, this distance will go down. If we increase the rho value, the Lipschitzness, the distance will go up. And if we increase B, increase the range that we're searching over, the distance will also go up.
Why are we concerned with the average of W instead of WT?
Yeah, this is a great question. So traditionally with stochastic gradient descent, let me scroll back up to here. The sort of the parameter estimate that we use is the very last parameter that we found. So when we calculate W2, we discard W1 and we discard W0. In this whole chapter of the book, however, they do not use this, this version of stochastic gradient descent that you may have seen before. Instead, they use that the parameter estimate that you should use is this W bar, and this is the estimate of what you should use as the minimum value of the function. And it's a little bit counterintuitive why you would want to use this instead of just the very last element, but it actually turns out that this has, in some cases, much better theoretical results. It's guaranteed to work in some situations when if you only use WT, the very last element of the search, there are situations where that is guaranteed not to work, but this one is guaranteed to work. So that's a great question, and we'll explore that a little bit more on Wednesday when we see compare all of those different formulas against each other. Any questions? Any other questions so far? Okay, then what I want us to do in the last few minutes of class is I'm going to skip ahead to the definition of stochastic gradient descent so that you can see this before doing your pre-lecture work for Wednesday. And this again is going to be potentially slightly different than, or the notation is potentially more confusing than notation that you've seen before. And so formally, what their notation is that you select a V T such that, so ST standing for such that, the expectation of V T given Wt equals the gradient of f at Wt. And then set Wt plus 1 equal to Wt minus eta Vt. So here the difference between, the real difference between this formula and the gradient descent formula is that instead of having gradient of f right here, we have some random variable which in expectation is equal to the gradient of f. For most learning problems, for most data mining problems, what we do is we set, again, f, it's f of, let me rewrite that, f of w equals the training loss of w plus lambda r of w. And this training loss, again, is equal to 1 over m sum from little t equals 1 to m loss of w comma z sub t. The z's here are our data points. This w, again, is the same w up here, plus lambda r of w. And so all I've done is substitute the definition for the training loss right here. And then if we were to select v sub t equals just one of these particular values, so equals the L of w comma zt, and then plus lambda r of w, then what we have is that this vt in expectation is going to also be equal to this, because we've just taken out, replaced the sum with one of its elements. And so this expression right here is what we would use up here. Yeah, on Wednesday, we'll see some more pictures of how the stochastic gradient descent and gradient descent algorithms work. We'll also see, start talking about the multi-dimensional case, and we will take all of these definitions, theorems that you do before class and apply them to actual learning problems to better understand how the learning problems, how stochastic gradient descent works on those learning problems. So that's it for today. And if stick around for a few minutes to answer any questions that that anybody has, but see you all on Wednesday.
Thanks, Mike.